Okay. Yeah, so the final thing here, practicing questions, practicing to read the lead and read the stem, and then look at the options after you've thought about an answer and see where your answer fits with the options that you've been given. And then the last thing here is study the topics that you have the hardest time with first. Study things that you find difficult first, instead of restudying things that you find easy or that come naturally to you. So for example, in the last unit, some of you may have been really good at cellular respiration, but then you had a hard time with maybe membrane transport or the initial chemical gradients and whatnot. If you study the topic that you have a harder time first, you just improve your performance on the exam because you're going to master across more topics, if that makes sense. Okay, so that's kind of just some tips I put together to share from what I'm seeing as I'm going over exams with other students. And so I really want you to kind of bear this in mind. If you're already doing great, if you've already got, good scores and good study strategies, this may just help improve. But if you're struggling, these are some things to consider along with some of the additional resources that I mentioned on Wednesday. All right. Okay. Excellent. So let's go ahead now. I'm going to go back into osmosis for just a bit because I also got some questions about osmosis and especially about the osmotic gradient and the osmotic pull. So I'm going to kind of just do a bit of recall on that topic and then a few practice questions that we left off on Wednesday, and then we'll head straight over into chapter 7, which is membranes, not membranes, sorry, which is membrane potential. All right, so back on the conversation of osmosis, let's start out by just kind of remembering what osmosis is. So we described osmosis as being, first of all, it's a passive motion or passive movement. So it's a passive movement. We can also call this diffusion, specifically of water across a membrane. We also said that it was not influenced at all by the charge or the membrane potential. And then we also said that water always moves along or down or with its concentration gradient. Alrighty, so that's kind of a basic definition. Let's look at an example here of let's take two cells or two scenarios here. On the left, we've got a higher solute concentration inside our cell. Whereas on the right, we've got a higher solute concentration outside the cell. And let's kind of just tabulate that down here at the bottom. So we've got solute concentration versus water concentration. You guys try to make sure that you arrive to class on time. I have to clear my annotation in order to enter this person in the chat. So just make sure that you're arriving to class on time. Okay. So we're kind of measuring the inside versus the outside. concentrations here. So let's tabulate the inside versus outside. And we'll do the same thing for the second scenario. Couple of things we want to mention here before we actually start going into this is that the membrane here is impermeable to the solute in question. When we talk about water moving, when we talk about osmosis, we want to bear in mind that water is moving because the solutes themselves cannot move. So as we speak about the movement of water, the solutes are not able to go through the membrane because the membrane is impermeable to the solutes that we're speaking about. Remember, when we were talking about, say, the concentration gradient, the chemical driving force of particles, those particles were able to go through the membrane. Here, as we're talking about water, only water is going through the membrane. So the membrane is impermeable to the solutes in question. Okay. And so let's look at our relative concentrations down here. So inside the cell, we have 1 mole particles dissolved. Outside the cell, we have a concentration of water of 100 mole. Excuse me, inside the cell. So this was both inside the cell. So 1 mole of particles dissolved and a water concentration of 100. Outside the cell, we have basically pure water, right? 0 particles dissolved and 102 moles in terms of the water concentration. Let's look at the other side. So similarly, we've got 1 mole inside, but now on the outside, we've got 2 moles of solutes dissolved. And so our water concentration is 100 inside, but then it's going to be slightly lower outside because we've got more particles. And so what we want to remember here is that the driving force for the movement of water is the concentration gradient of water. Let's actually go ahead and make a note of that. So the driving force for the movement of water is always the concentration gradient. And so basically we have this scenario where the particles here want to be at equilibrium. And because they cannot move through the membrane is impermeable to the solutes, water has to move instead in order to bring these two solutions to equilibrium. And so water is going to move according to its concentration gradient. In the first scenario, it's going to move from outside to inside the cell. And what that will do is that will bring the two solutions to equilibrium because water is going to pretty much dilute the concentration inside the cell. And so we can say that the osmotic pull here is from the outside of the cell to the inside of the cell. And so what that basically means is that we have a higher osmotic pressure inside the cell. Remember, the osmotic pressure is the force with which water is moving. And water is really moving towards the higher solute concentration and away from the higher water concentration. So the osmotic pull is higher on the inside, and it's got osmotic pressure here. This should be pressure. My stylus is acting up. Okay. And then there's a decreased osmotic pressure on the outside. Okay. So again, what this means is that we have a higher osmotic pressure, and think about osmotic pressure as a pull, as a drag. Solvents are dragging water towards them. So we've got a higher pressure inside and a lower pressure outside. And so the osmotic pressure gradient is going to be from the outside to the inside, where this water is being pulled from the higher concentration into the lower water concentration. So there's a difference here. And if you think about it from either side, Water is moving down its concentration gradient, but it's going to be moving against the solute concentration gradient, okay? So we can think of it from either perspective. It's moving from high to low in terms of the water gradient, but it's moving from low to high in terms of the solute concentration. And the same is true on the opposite side, but here we've got a lower osmotic pressure inside because we have less solutes inside. And we've got a higher osmotic pressure outside because again, this is the side where we have the higher solute concentration. And so you can also think of this as the solutes pulling water towards them in order to dilute the side that has the higher solute concentration and help to bring both the solutions to equilibrium, okay? So this is what we mean when we talk about the osmotic pressure and the osmotic pressure gradient. And if we really look at it, the osmotic pressure gradient is going to be the opposite of the actual water gradient. The solute concentration too will be the opposite of the water gradient. And just to indicate this here, the direction of water movement will be from inside the cell to outside the cell, because again, the side that has the higher solute concentration also has the higher osmotic pull, and that's the side that's pulling water towards it, whereas the side that has the lower water concentration is the lower solute concentration, excuse me, is the side from which the water is being pulled. Okay, and so this is basically what we talked about as far as osmosis, that driving force where water moves down its concentration gradient because the solutes cannot move themselves. Important to remember is that the membrane is impermeable to the solutes, otherwise the solutes would move. The solutes would move to bring those two solutions to equilibrium. But because the solutes cannot move, then the water has to move to equalize both of those solutions, inside and outside.